Hello everyone. Today we are going to start with the core part of your theory syllabus. And the first chapter which we start with is units and measurements. Basically we know that physics is a quantitative science where we measure various physical quantities. We need to measure a number of quantities like size of objects, volume of liquids, amount of matter, weight of vegetables, body temperature, length of cloth, distance between stars, distance between planet and all. So when we consider a measurement always involves a comparison with a standard measuring unit which is internationally accepted. The measured quantity is expressed in terms of number followed by its corresponding unit. For example, 5 meter, 5 kg, 5 liter, 5 second, etc. For different quantities, there are different systems of units. For length, we consider, for example, meter. For time, we consider second. For mass, we consider kg. It means there is always one standard measure for each quantity and we called it as a unit. In our earlier standards, we have come across various systems of units. Here we are going through 4 number of systems: CGS, MKS, FPS and SI, where C stands for centimeter, G stands for gram, S stands for second. So CGS means centimeter gram second system. Similarly, MKS meter kilogram second system, FPS foot pound second system and SI is system international of units. This international systems of units is called as SI unit. As the SI units use decimal system, conversion within the system is very simple and convenient. When we consider the quantity which can measure, it's called as the physical quantity. There are basically 2 types of physical quantities. One is independent and one is dependent. In detail, the physical quantities which do not depend upon other quantities for its measurement are called fundamental quantities. And other than fundamental quantities, all quantities may be derived from fundamental units are called derived quantities. So when we consider fundamental quantities, at that time they are independent one. We can measure them directly either with the instrument or with the unit. But it's not possible about derived quantities. Why? Because of they require the help of fundamental units, fundamental quantities for their derivation. Basically, there are 2 main supplementary plus 7 basic main quantities. Totally, there are 9 fundamental quantities and rest all quantities are derived one. So when we consider these fundamental quantities which contains length, mass, time, temperature, electric current, luminous intensity and amount of substance, these 7 are called as basic or main fundamental quantities plus 2 supplementary are plane angle and solid angle. As we already discussed, there are different units for different systems. As per that, for length we consider meter, for mass we consider kilogram, for time it's second, for temperature it's Kelvin, for electric current we consider ampere, for intensity it's candela, for amount of substance we know mole, then for plane angle it's radian and for solid angle it's steradian. Other than these 7 plus 2, 9 quantities, rest all are derived one. For example, if I consider volume, volume generally given by meter cube, so it requires the help of length to derive its unit. For density, we know that it's mass upon volume. Mass divided by again volume is length cube. So density can be represented as mass upon length cube. So its unit is kg per meter cube. Velocity is meter per second, that is length upon time. Force is F is equal to ma, mass into acceleration. So when we consider other than these 9 quantities, each and every quantity requires the help of fundamentals 1. Now, when we consider SI unit, at that time there are some rules to use that unit. Let's discuss one by one. The first one, unit of every physical quantity should be represented by its symbol. So for meter, generally we use M. For Newton, we use N. For centimeter, we use cm and etc. Second one, full name of a unit always start with a smaller letter even if the name is after a person. For example, it's Newton, Joule, Erg, etc. So when we consider such kind of unit, at that time for whole name we use a small letter as an initial one, but for symbolic representation we use a capital letter. So we represent Newton as a capital N, we represent Joule as a capital J. Next one, symbols for units do not take plural form. For example, we can write 20 Newton, not 20 Newtons. We can write 2 meter, not 2 meters. Next one, symbols for units do not contain any full stop at the end of recommended letter. It means after writing a unit, do not place any full stop. Next, the units of physical quantities in numerator and denominator should be written as 1:. For example, the unit of acceleration, as we know, it's meter per second square, or you can write it as a meter second raised to minus 2, but you are not supposed to write as a velocity upon time. That's why meter per second per second. This one is the wrong one. Next one, use of combination of units and symbols for units is avoided when physical quantity is expressed by combination of two. For example, the unit joule per kg Kelvin is correct, while joule per kg Kelvin is not correct. Check again. Here, J stands for joule. You are not supposed to write the full form of that J. Next one, a prefix symbol is used before the symbol of the unit. And last one, space or hyphen must be introduced while indicating multiplication of two units. For example, meter per second should be written as meter second raised to minus 1 or inverse, or meter slash s raised to minus 1, but you are not supposed to write as a meter s raised to minus 1. Why? Because of ms will be read as millisecond. So when you are supposed to write these kind of units, you must take a gap or space in between that two alphabets. Next one, there are few basic systems or few basic methods with which we can measure length, we can measure mass, we can measure time. Let's start one by one. Measurement of distance to stars. We know that sun is the star which is closest to the earth. The next closest star is at a distance of 4.29 light years. For this, we use the parallax method. The parallax measured from two most distant points on the earth for stars will be too small to be measured. And for this purpose, we measure the parallax between two farthest points along the orbit of the earth around the sun. How to measure the size of a planet or a star? We know that if we consider there is angle between two directions which are diametrically opposite points of the planet are viewed through a telescope, then let us consider capital D is a distance of a planet, and when we can calculate the diameter of planet, at that time we will get alpha is equal to small d upon capital D. That small d is alpha into capital D. We know the distance of a planet which is given by capital D. We know the angle denoted by alpha. It is the angle between two directions when two diametrically opposite points of the planet are viewed. So in this way, we can easily find out value of small d, which is diameter of a planet. The next one, measurement of very small distances. How to measure it? When we consider to measure the size of atoms or molecules, the conventional apparatus like vernier caliper or micrometer screw gauge will not be useful. Therefore, here we are using the electron microscope or tunneling electron microscope to measure the size of atoms. We already had discussion on parallax method. For the large distance such as the distance of a planet or a star from Earth cannot be measured directly with meter scale. So, in this case, parallax method is used. How to use it? Let us consider a small experiment to get to know about the parallax. What is effect of parallax? When we hold our hand in front of our eye, there is a difference between positions when first left eye closed and then right eye closed. Definitely we'll find our hand appears to move against the background. This effect is basically called as parallax. It is defined as the apparent change in position of an object due to a change in the position of an observer. By measuring the parallax angle and knowing the distance between the eyes E1 and E2, we can determine the distance of object from us. For example, here I can measure OP as E1 E2 divided by theta. You can see an example over here. There are 2 points A and B on the surface of Earth at two different positions and separated by a straight line at distance B. You can check it in the figure. Two observers at these 2 points observe a distant planet S simultaneously. Let's measure angle ASB between two directions along which the planet is viewed at these 2 points. This angle is represented by theta. So, as per we discussed, E1 E2 upon theta can be derived as capital D is equal to small b upon theta, which is called as the parallax method to measure the large distances. Now let's move towards measurement of mass. As we all know, the basic unit to measure the mass is kilogram, and according to new concept, kilogram mass can be described in terms of the amount of current which has to be passed through an electromagnet so that it can pull down one side of an extremely sensitive balance to balance the other side, which holds the strong 1 standard kg mass. So when we consider what is kilogram exactly, it is defined in terms of magnitude of electric current. This electric current can be used to make an electromagnet. So when we are dealing with the mass of atoms and molecules, kg is not useful, or it is an inconvenient unit for this measurement. So their mass is measured in atomic mass unit. It is very easy to compare mass of any atom in terms of mass of some standard atom which has been decided internationally to be C⁻12 or carbon atom. The unit of carbon atom is atomic mass unit, which is equal to 1.660 into 10 raised to minus 27 kg. Moving towards next point, let's start with the measurement of time. As we all know, the SI unit of time is second. For many years, duration of one mean solar day was considered as a reference. It is the average time interval from one noon to the next noon. Generally, average duration of a day considered as a 24 hours. 1 hour contains 60 minutes and 1 minute contains 60 seconds. It means in 24 hours there are 86,400 seconds. Accordingly, a second was defined as 1 by 86,400th part of a mean solar day. So when we consider these measurements systems of length, time and mass, it is always important to measure it in a different forms. Now, according to these three basic and fundamental units or quantities, we can find out the unit of any other quantity. It means we can find out raised to powers, we can find out dimensions, we can find out its drawbacks too, which are called as dimensional analysis. Here we go with next point. The dimensions of a physical quantity are the powers to which the concerned fundamental units must be raised in order to obtain the unit of a given physical quantity. I'll explain it in a simple manner. If I consider velocity, the dimensional formula is displacement upon time. Now, let's ask a question to this quantity. Is it independent one? Yes, it is. Is it depend on mass or time? No, it's not. So, the mass quantity and time quantity is absent over here for the displacement. So, we can write for displacement it's only L raised to 1, M raised to 0, T raised to 0 divided by time. Time is independent with mass and length. So that both quantities are absent over here. So for time, I have to write only T raised to 1. So L raised to 1 divided by T raised to 1 can be represented as L raised to 1, M raised to 0, T raised to minus 1 in square bracket form, because of this is the basic important law for this, that dimension has to be written in the form of square bracket. Now, let's discuss the formula for velocity gradient. What is velocity gradient? When anything changes with distance, that is called as gradient. So, velocity gradient is velocity upon distance. Velocity, here we have L raised to 1, M raised to 0, T raised to minus 1 divided by distance, again L raised to 1. So, L raised to 1, T raised to minus 1. From denominator, it's L raised to minus 1 into the numerator. So, L1 minus 1, L raised to 0, M raised to 0, T raised to minus 1. In this way, you can write n number of things. You can find out where dimensional formula for charge also. Charge is equal to current into time, as current is the fundamental quantity. So, you can express it directly in the form of I or capital A as an ampere one. So, I raised to 1, T raised to 1, rest all quantities are 0. For example, density, mass upon volume, it's L raised to minus 3, M raised to 1, T raised to 0. For acceleration, for momentum, for any quantity, either they are fundamental or they are derived, doesn't matter. We can find out dimensional formula with the help of raised to powers, with the help of these basic quantities, that length, mass and time. Now, there are few uses of dimensional analysis. Let's discuss one by one. The first one, we can check the correctness of physical equation. How to check? As per our knowledge, in maths we can check the derivation. Either both sides are equal or not. And the basic equation, if I have V is equal to U plus AT, then how to check and what to check? I have to check if both sides are having same dimensions or not. And if the both sides and each quantity having the same dimension, then that equation is dimensionally correct equation or physically correct equation. For example, U plus AT is equal to V. V stands for velocity, U stands for velocity, AT, A stands for acceleration, T stands for time. The rule is, in any equation relating different physical quantities, if the dimensions of all the terms on both the sides are the same, then that equation is said to be dimensionally correct. Let's start. For velocity, we know that it's meter per second. For meter, L raised to 1. For second, it's T raised to 1. So, finally, velocity having dimension L raised to 1, M raised to 0, T raised to minus 1. U is again velocity, so its dimensions are L raised to 1, M raised to 0, T raised to minus 1. We know that acceleration is equal to velocity divided by time. So velocity is equal to acceleration into time. So A into T again is the equivalent value of velocity only. So dimensions of RHS are equal to dimension of LHS. As the both dimensions are same, this equation is dimensionally correct equation. You can find it out for total energy is equal to kinetic energy plus potential energy. You can derive it for V square is equal to U square minus 2AS. You can derive it for V is equal to UT plus half AT square also. So in this way, we can check all kinematical equations whether they are dimensionally correct or not. The second use of dimensional analysis is to establish the relationship between related physical quantities. What it means? If I know that there are few physical quantities which are related to each other. Let us start with one basic example. If I have the period of time T of oscillation of a simple pendulum depends on length and acceleration due to gravity, then we have to derive the relation between them. According to the dimensional analysis, I know dimension of these all terms. Now how to use it? Let's discuss. First, note down the things which are dependent on each other. Here, the time period of oscillation of a simple pendulum depends on length. So let's note down T is proportional to A. Then acceleration due to gravity. Second, note down T is directly proportional with G. Now we don't know the raised to powers, so we'll take L raised to A and G raised to B. So overall the equation will come T is proportional to L raised to A, G raised to B. Let's remove this proportionality sign. We'll get T is equal to K L raised to A, G raised to B, where K, as per our knowledge, is a proportionality constant. Now we know that there are separate dimensions for T, for L and for G. Let's introduce them. For T, time period, only T raised to 1. For length, L raised to 1. And for G, G is acceleration. So L raised to 1, T raised to minus 2. Mention these raised to properties as it is. Now as we know that A raised to N raised to A is A raised to N A. So L raised to 1 raised to A becomes L raised to A over here, and L raised to 1 T raised to minus 2 raised to B becomes L raised to B L raised to minus 2B. Now we know that A raised to X into A raised to Y gives us A raised to X plus Y. According to this basic law, we can write L raised to A plus B T raised to 0 minus 2B. So, L raised to 0 T raised to 1 is equal to K L raised to A plus B T raised to minus 2B. Again we know the basic law that A raised to X is equal to A raised to 5, then X is equal to 5. In this way, let's compare both sides. L raised to 0 is over here, L raised to A plus B is over here. So, after comparison, A plus B is equal to 0, we can write. Similarly, T raised to 1, T raised to minus 2B. I can compare both sides and write minus 2B is equal to 1. So, A plus B is equal to 0, A is equal to minus B, and minus 2B is equal to 1. So, B is equal to minus half. Let's substitute these values over here. A is equal to minus B, B is equal to minus half. So, A becomes plus half. Let's substitute value of A and value of B to this equation. T is equal to K L raised to, in place of A I'll use half, in place of B I'll use minus half. So T is equal to K L raised to half G raised to minus half. That's why T becomes K under root L by G. Now you can keep it as it is also, or if you know the value of K, then you can substitute that value in given equation. For simple pendulum, we know that K is equal to 2 pi. Therefore, T is equal to 2 pi under root L upon G. So in this way, with the same skeleton, you can find out the relation between any two related physical quantities. The next use of this is to find the conversion factor between the units of the same physical quantity in two different systems of units. For example, in 9th, 10th standard, you know that from that syllabus, the unit of force, SI unit is Newton, CGS unit is dyne. You know the relation between both of them. 1 Newton is equal to 10 raised to minus 1 Newton is equal to 10 raised to 5 dyne. So we can derive that equation with the help of dimensional system or dimensional analysis. Here we are going through the quantity work. For work we know that work is equal to W is equal to force into displacement. So according to that, the dimensional formula becomes m raised to 1, L raised to 2, T raised to minus 2. According to this, the quantity having unit kg meter square per second square, or we called it as a joule. Now we know that SI unit can be written as, for kg it's gram, for meter it's centimeter, and for second it will be same, so it's second only. So as SI unit is kg meter square per second square, CJS will be gram centimeter square per second square. We called it as a erg. Let's start. Now we consider M1, L1, T1 as for SI unit and M2, L2, T2 as for CJS unit. Let's start. We want to find out value of X, that M raised to 1, L raised to 1, T raised to minus 2, and similarly M2 raised to 1, T2 raised to 2, T2 raised to minus 2. What is relation between both of them? 1 joule is equal to how many ergs? We are going to find it out. So let's start. Divide this term by first X is equal to M1 raised to 1, L1 raised to 2, T1 raised to minus 2 divided by M2 raised to 1, L2 raised to 2, T2 raised to minus 2. Now we know that A raised to X divided by B raised to X can be written as A upon B raised to X. So M1 upon M2 raised to 1, L1 upon L2 raised to 2, T1 upon T2 raised to minus 2. Now, suffix 1 indicates SI unit, suffix 2 indicates CGS unit. Let's introduce units of mass, length and time in the form of CGS and MKS units. For M1 it's kg, for L1 it's meter, for T1 it's second, for M2 it's gram, for L2 it's centimeter, for T2 it's second. So this equation can be written as X is equal to kg upon gram raised to 1, meter upon centimeter raised to 2, second upon second raised to minus 2. So either convert this kg in the form of gram or gram in the form of kg. Similarly for meter and centimeter. So we can write 1 kg is equal to 10 raised to 3 grams, 1 meter is equal to 10 raised to 2 centimeter. So 10 raised to 3 gram upon gram, 10 raised to 2 centimeter upon centimeter, as well as second gets cancelled. So 1 raised to minus 2. This term can be cancelled or negligible. So gram cancel, centimeter cancel, 10 raised to 3 raised to 1, 10 raised to 2 raised to 2. So 10 raised to 3, 10 raised to 4. Combine leaving 8, 10 raised to 7. So in this way, 1 joule is equal to X ergs. X is equal to 10 raised to 7 according to dimensional analysis. So this equation will become 1 joule is equal to 10 raised to 7 erg. So in this way, there are 3 uses of dimensional analysis on the basis of which First one, we can find out correctness in physical equation. Second one, we can derive the relation between related physical quantities. And third one, we can find the conversion factor between units of the same physical quantity into different systems of units. Now, according to these all things, there are few limitations also for this dimensional analysis. Let's start one by one. The first one, the value of dimensionless constant can be obtained with the help of experiments only. You cannot find it out with the help of dimensional analysis or its any one use. Second one, dimensional analysis cannot be used to derive relations involving trigonometric, exponential and logarithmic functions as these quantities are dimensionless. Third one, these methods are not useful if constant of proportionality is not a dimensionless quantity. Next one, if the correct equation contains some more terms of the same dimension, it is not possible to know about their presence using dimensional equation. So in this way, you can find out dimensional analysis with few limitations, and you can find out any formula, any unit of any fundamental or derived quantity. In next topic, we are going to discuss about next parts like how we can add or how we can subtract any two-dimensional quantities. Are there any possible errors or methods to minimize that terms and all? So let's moving towards next session tomorrow. Thank you.